In Interstellar, Cooper lands on a planet where 1 hour costs him 7 years of his daughter's life. 1 hour equals 7 years. That's a ratio of about 61,000 to 1. Most viewers file this under Hollywood exaggeration, physics stretched beyond recognition for dramatic effect. It isn't. The math works perfectly for the black hole Kip Thorne designed for that film. And something stranger still, a weaker version of this same effect is warping time around the phone in your pocket at this exact moment. GPS satellites orbiting Earth run their onboard clocks about 38 microseconds fast every day compared to identical clocks on the ground. That sounds trivially small, but GPS works by timing signals to nanosecond precision. Ignore that 38 microsecond drift, and by tomorrow, your map app would be off by roughly 11 kilometers. Within a week, the entire system collapses into uselessness. GPS engineers must program Einstein's corrections into every satellite, or navigation dies. Here's the puzzle that should stop you. Why would a clock on a satellite tick at a different rate than a clock in your kitchen? They're measuring the same thing. Seconds, the passage of time. Yet they disagree. What does it even mean for time itself to flow at different speeds in different places? Einstein figured this out in 1915, though humanity took decades to believe him. His insight wasn't about satellites. They didn't exist. It was about gravity. Not gravity as a force reaching across space to pull masses together, but gravity as the shape of space-time itself. Start with what everyone knows. Heavy things attract other things. Newton described this beautifully. A star pulls a planet pulls a moon. But Newton's description left something embarrassing unexplained. How does the sun reach across 93 million miles of vacuum to tug on Earth? Newton himself called this action at a distance and admitted he had no mechanism. Einstein's answer was radical. The sun doesn't reach across space. The sun bends space. And not just space, space-time. The fabric in which all events occur, the very thing that defines where and when, curves in the presence of mass. Picture a bowling ball on a stretched rubber sheet. The ball creates a depression. Roll a marble nearby and it curves toward the bowling ball, not because the ball is pulling it, but because the sheet itself is warped. The marble follows the only available path through bent geometry. That's gravity. But here's where intuition fails. The distortion isn't merely spatial, it's temporal. Near a massive object, time itself runs slower. Think about what moving through space-time means. Standing perfectly still, you're not moving through space, but you're absolutely moving through time at 1 second per second. Einstein's equations revealed something shocking. Mass warps the direction through space-time that time points. Near a heavy object, clocks tick slower, not because something is wrong with them, because the geometry of time itself has changed. For decades, this remained theoretical elegance. Then came atomic clocks precise enough to test it. In 1971, physicists loaded cesium clocks onto commercial jets, eastward and westward around the world, then compared them to identical clocks left on the ground. The airborne clocks, which had experienced slightly weaker gravity at altitude, showed measurable time differences. Exactly as Einstein predicted. Modern tests are astonishing. By 2010, optical clocks achieved such precision that raising one just 33 centimeters, the height of a single stair step, produced a detectable difference in the flow of time. Climb one step and your head ages faster than your feet. The difference is absurdly small, unmeasurable by any human sensation. But real. Now return to Interstellar. Cooper's team lands on Miller's planet, orbiting terrifyingly close to Gargantua, a supermassive black hole containing roughly 100 million solar masses, spinning at nearly the maximum rate physics permits. Kip Thorne, the Nobel Prize-winning physicist who designed Gargantua for the film, worked backward from the 1 hour to 7 years ratio. He calculated exactly where Miller's planet had to orbit. 7 years contains about 61,300 hours, so time on Miller's planet runs 61,000 times slower than far from the black hole. General relativity provides exact equations, relating gravitational time dilation to proximity to extreme mass. For that 61,000 factor, Miller's planet must hover just barely outside Gargantua's event horizon, deep in the region where space-time has warped so severely that time practically stops. Thorne ran the numbers. The orbit is physically possible. Interstellar isn't taking dramatic license with time dilation. It's applying general relativity honestly. GPS brings this cosmic phenomenon into your hand. Those 24 satellites orbit roughly 20,200 kilometers up. At that altitude, gravity is weaker, so their clocks tick faster, by about 45 microseconds daily. But the satellites also move at 14,000 kilometers per hour relative to ground, and special relativity says moving clocks run slower, by about 7 microseconds daily. The net effect? Satellite clocks gain 38 microseconds each day. What does this mean practically? GPS locates you by measuring how long signals take to travel from satellites to your phone. Light covers about 30 centimeters per nanosecond. A timing error of 38,000 nanoseconds, 38 microseconds, translates to roughly 11 kilometers of position error. Every day, accumulating. Engineers don't let this error build up and then correct it. They pre-compensate. Before launch, the atomic clocks aboard GPS satellites are deliberately set to tick slightly slower than ground clocks. Once the satellite reaches orbit, the combination of weaker gravity speeding clocks up and orbital velocity slowing them down brings everything into synchronization with ground time. This is Einstein's revenge on intuition. Clocks must be detuned on Earth to function correctly in space. But here's what physicists still cannot explain. General relativity describes gravity as smooth geometry, curved spacetime that particles glide through. Quantum mechanics describes everything else, matter, forces, light, as discrete, probabilistic, and fundamentally granular. These two frameworks refuse to unify. At ordinary scales, this doesn't matter. Gravity dominates planets and galaxies, quantum effects dominate atoms. The realms barely overlap. But inside black holes, near the singularity where all the mass concentrates, both theories must apply simultaneously, and both break down. What happens to time at the smallest scales? Does time become quantized, grainy like energy levels in an atom? Does it emerge from something deeper? Or does the question cease to make sense entirely? No one knows. The interior of a black hole, beyond the event horizon, is where general relativity points toward infinity and quantum mechanics offers only silence. Interstellar used this mystery deliberately. Cooper enters Gargantua and encounters what he calls the Tesseract, a space where time is laid out like a physical dimension, explorable and navigable. Pure speculation, of course. But the film asks the real question physicists can't yet answer. What is time, fundamentally? Is it a dimension woven with space, as relativity insists? Or a universal background parameter, as quantum mechanics assumes? At the deepest level, they cannot both be right. Every time a phone calculates a route, engineers have accounted for time running differently at 20,000 kilometers altitude. Every hour Cooper spent on Miller's planet, time dilation stole years from his daughter. Same principle, different scale. The universe provides no master clock, ticking identically everywhere. Time is local, shaped by mass and motion, unique to every point in the cosmos. Einstein didn't just reveal how objects fall, he revealed how reality ages, differently, everywhere, always. The second you experience right now is your second, sculpted by Earth's mass beneath your feet and your velocity across its surface. Somewhere near a neutron star, that same second stretches into hours, near Gargantua, into years. Time isn't the background against which the universe happens. Time is part of what the universe is made of, and gravity bends it like light through glass. Like if this was interesting, hit the subscribe for more and turn that notification bell on.